Okay, so this is the second FRQ of the Unit 11 project. So, relevant equation V equals IR. And then we also are going to need to know the equivalent resistance in series is R1 plus R2 plus R3 and so on and so on. And then R1 over equivalent resistance of parallel is 1 over R1 plus 1 over R2 and so on and so on for however many resistors there are. Okay, so let's jump in here and start solving. So calculate current measured in ammeter. So we're going to leave from the positive, go through R1, and then it splits into two branches. There's going to be no current going through R3 because it's in parallel with an ideal wire. So when this is open, nothing is going to, no current. When the switch is open, no current is going to be going through R3. So we're going to have that, and then we're also going to have it from there. So we have to calculate R2 for, and that's just going to be 6 plus 12. That's 18 ohms. And then we have to calculate that in parallel with R5. That's going to mean 1 over R parallel equals 1/18 plus 1/6. And that's going to be 4/18. And then, so that means R parallel four equals 4.5 ohms. Okay. And then we have to remember, so that's, this is now 4.5 combined, and then that's with the 2, so our total equals 2 plus 4.5 equals 6.5 ohms. And then we have to use Ohm's law to find current going through A1. I equals V over R. That's just rearranging V equals IR. IA1. And have our battery of 20 volts given to us. And the resistance of A1, 6.5. And then that's going to be about 3.1 amps. That's going to be 3.1 amps. Okay. And now to calculate potential difference measure voltmeter V. Well, we said that the voltmeter is across R3, which is 12 ohms, but when the switch is open, there's no current going through R3. So that means I3 is 0, and that's going to mean V equals 0 times 12 equals 0 volts. So this is 3.1, and now this is 0. Now, when the switch is closed, calculate current measured through ammeter 1. All right, well, let's draw it closed now. That. And then now R2, R3, R4, and R5 are all in parallel with each other. So we're going to do 1 over 6 plus 1 over 12 plus 1 over 6 plus 1 over 12. Oops. Plus 1. And then that's going to equal 6/12. And that means our parallel is 12 over 6 or 2. And then again, so we just calculated these two combined, but we still have R1 in series with it. So our total is 2 plus 2. That's 4 ohms. Okay. And then now we're going to calculate current going through A1. Our voltage is the same. IA1, I'll put a CL for close. Now that's going to be 20 over 4. Remember last time it was 6.5 over 6.5. And so now we're going to get 5 amps instead of 3.1 like we got when it was open. Now we're going to calculate voltage through the voltmeter when it's closed. Well, now since it's closed, it won't be 0 because there's current going through it. And this is pretty simple. We have our voltage. We have our current, 5 amps here. And then that's going to be times the 5 amps is going to go, oh, wait, sorry. Through voltmeter V is okay, sorry. So what we're going to do is calculate voltage drop across R1, and that's going to be V1, because we know that 5 amps goes across that. 5 amps times the 2, and that's going to be 10 volts. And then the parallel block is there, since this is potential difference, that's going to be the 20 volts from the battery minus this 10 volts. And that's going to be 10 volts. I was trying to calculate it just looking at here, but you have to calculate potential difference through here. And now C is asking, okay, so current is replaced with the switch is now replaced with ammeter 2. So it's a closed switch and can measure the current, if any, between 2 points. Calculate the current measured by ammeter 2. Okay. Well, when the switch is closed, they're all in parallel. And then points X and Y would then be at the same potential, because they're in parallel. And that's a rule. So our potential difference would be 0. And that would make the current 0, because V equals I times R. So and our total resistance would be the same as before. It was what was it before when we calculated it? It was 4 ohms, but and our V is going to be 0, and that would mean I has to be 0. So current measured through ammeter 2 is going to be 0. That's easy. Indicate the direction of current through ammeter A2 as left, right, or undefined because the current is 0. Well, if the current's 0, it'd be undefined. There can't be if there's no current, there can't be a direction to the current. So it's going to be undefined. Okay, and now it's replaced with switch S and capacitor. Okay. Calculate the charge stored on the positive plate of the C a long time after switch S is closed. Okay. Well, now we're going to need to use our friendly equation Q equals CV. Well, C equals 12. So that would be micro. Oh, C is 12. Okay, so then we could just calculate our charge. That's pretty easy. They give us C. Q equals, and that since it's micro, it's going to be times 10 to the negative 6. And then that's going to be times 10. Because our V that we calculated in the second part of B, we calculated voltage XY is going to be 10, because remember we did 20 minus the potential difference across R1 is 10. And then we're going to get, we multiply that, we calculate that, and we get 1.2 times 10 to the 4 coulombs. Okay. And then which point, X or Y, is at a higher electric potential? And and it's important that we see in one, it says a long time after switch S is closed. So that means the capacitor is fully charged and the voltage across it would equal the steady voltage between X and Y. And then which point is at a higher potential? So the capacitor's positive plate is connected to Y and its negative plate is connected to X. And the positive plate of a charged capacitor is at the higher